Hey everybody, in this lesson we are going to start learning how to analyze data, actually calculating statistics that can help us take a numerical summary and actually quantify, attach some numbers to it, things we can interpret and use to our advantage. Today our topic is measures of central tendency. So let's get started. So when you have a set of numerical data, it's often convenient to use a central value to summarize a set of data. So like your report card, for example, has two. You probably have heard of these, median and mean. There's a third measure of central tendency called the mode as well. So these three M's, mean, median, and mode. I bet you guys have all heard of these. You've probably all worked with them already as well. Actually, usually it's mean, median, mode. Are the three. So to start off, a little quick review on finding these if you've kind of forgotten those skills. So the mean is defined as the sum of all values of a variable divided by the number of values. And later on, there's going to be an important difference between the means of a sample and a population. And so we're going to have two different kind of notations for mean depending on our situation. If we are finding the mean of a population, we use this notation. We use the Greek letter mu. And to find the mean, we add up all the data values. So remember from our discrete distributions unit, this Greek letter sigma means sum, and x is just the data values. So we add up all the data and we divide by, I'm going to say capital M. So this is the population size. When we're finding the mean of a sample, we'll use the following notation. We'll use x bar instead of mu, so x with a little bar on top. You still find the mean the same way. You add up all the values you have, and this time we'll divide by, we'll call it little n, and this is our sample size. Our next measure of central tendency we're reviewing is the median. It's the central value of a data after they're ranked. So that's important, is that you have to have the data from lowest to highest or highest to lowest. In the case of two central values, the mean is the average of these two values. So what do I mean by that? Let's just do a quick, easy example and show this. So we're going to find the mean and median for these data sets. So we'll just assume that this is it doesn't matter. Assume it's a population. So for the mean, remember we're adding up all the data values, dividing by the number of values. In this case, 7, 11, 18, 26, 30, we have 39. In case I added incorrectly, 11, 18, 26, 30, yeah, 39 divided by 8 values. And so I believe that's 3.875, but I'm just going to double check here at home. 4.875. Too early to be doing mental math. 4.875. For the median, we have to have the data sorted, lowest to highest. Lowest is 2, and then we have a 3. We have 2 4s. So this is actually even a good habit to get into, a 6, a 7, and 8 before you even do any statistics. So here, the median is like the middle number or the average two middle numbers. Is there a middle number for these data sets or for this data set? So you can look at, we have 8 values. Is there a middle number? And the answer is no. There's 2 middle numbers, right? So the median is actually going to be the average of those 2 middle numbers. So the median, 4 plus 5 divided by 2. You could have done that mentally. The median for that set of data is 4.5. If you want to try the second one on your own, feel free to pause the video and try that. I'm going to just get into good habits and sort my data first. So 2, 3, 4, 4, 3, 5, 6, and 9. All right, so my mean, sum of the data divided by number of values. So here, 5, 13, 23, 28, 34, 43. We have 9 values in this case. think it's 43. Always not a bad idea to double check if you're using mental math like me here. 14, 23, 29, 30. Yeah, 43 divided by 9. So this will be a little bit below 5, about 4.8. And in this case, there is a middle number because the number of data values is odd. When that's the case, when you have an odd number of values, you always have a middle number. The middle number is this 5. The median is 5. When you have an even set of data values, you will always have 2 middle numbers and you'll find the average, and that holds all the time. So a little quick review on finding mean and median. The mode is the most frequently occurring data value or values. A set of data can have one mode, it can have none, or it can have several. There's a few different cases. So knowing that the mode is the most frequently occurring value or values, why don't you try finding the mode or modes for these 4 little mini sets of data. You can do these on your lesson sheet, unpause when you're ready, and let's see if you get this idea of mode. There's definitely a couple, I'm not going to say trick questions here, but maybe curveballs in case you haven't worked with mode in a long time. So the first guy, the mode's pretty easy to spot. 4 occurs more often than all the others. If you look at B, there's 2 numbers that occur more often than all the others. There's 2 modes. In this case, the modes are 3 and 4. There's 2 of them. 3 and 4 occur twice. The rest occur only 1 time. If we look at part C, 1, 2, 3, 4, 5, or 6, no value occurs more often than another value. It's like a tie. There's no mode. Now, I anticipate that most of you guys probably got A, B, and C. My anticipation for D is that some of you guys might have said that 1, 2, and 3 are all modes because they occur multiple times. But in this, I'd ask you, do any of those values occur more often than any of the other values? No, it's a tie between all 3. This is an example of a set with no mode as well. So mean, median, and mode. So let's talk about outliers. So when you guys were in grade 9, you might have talked about an outlier as, you're making a scatter plot, you're trying to see a trend, make a line of best fit perhaps. An outlier is a point that is really, really far away from your scatter plot. Like, if I can find my cursor, there it is. If you have a scatter plot showing a clear trend, and then you got this guy way up here, that is an outlier. So an outlier in a set of data is similar. It's significantly different from the rest of the points. So here's a little visual of a histogram of data values, and you can see that 15 or 14, whatever that is significantly different than all the other guys clustered around 6 and 7. So in your grade 9 course, you didn't really have a formal way to say, hey, that's an outlier. You just said that guy looks like it's different. I'll call it an outlier. And right now, we're going to do the same thing. In our next lesson, we'll actually develop a formal way to identify whether something's an outlier or not. But for now, we'll just kind of loosely say, okay, I think everyone would agree in this data set here, this example, 12 is definitely an outlier. It's a lot different from those low numbers. So I want you guys to find the mean and median for these 2 sets. 1 has the outlier, and B, the outlier has been removed. I want you to find the mean and median for both and see which one is affected more. So I'm just going to use, nothing in here indicates it's a sample or a population, so I'll just use mu. Add up all the values. You don't always need to write the notation there. 3, 6, 9, 13, that's 25 over 6. Just double checking that. And that is about 4.2, but I'm going to double check because I've already made a mistake earlier today. Yeah, it's about 4.2. And then the median, this data set's already sorted. There are 2 middle values, these 2 3s. So the median is the average of those 2 3s. So I just actually might show that. I'm sure many of you guys just said, okay, it's obviously going to be 3. But just emphasizing it's the average of those 2 middle values. So the mean, 4.2, the median's 3. But let's see what happens when you remove the 12. How do those things change? So the new mean, we only have 5 values. those values add up to 13 divided by 5. 13 divided by 5 is 2.6 exactly. The median, we now only have 5 sets of values. There is a middle number. It is this 3. The median is 3. So if you look at it, removing the outlier did not change the median here, but it changed the mean significantly. Now, this won't always be the case when you remove an outlier. Like, the median doesn't always stay the same. But the principle of this is, and hopefully you're convinced, is that if you remove an outlier, the mean gets affected more than the median. So outliers affect the mean the most. So this is why on your report cards, you might have a mean and a median, because if you only included the mean, and I'm sure most of you guys, you know, there's people in your class, they might only come every once in a while, or you know that they're not really working, or for whatever reason, there's people in your classes that have marks in the zeros, the tens. You know, there won't be a lot of them, but it happens sometimes, and it would almost be unfair to just show the mean to say how your class is doing, because you usually always have a few of those really low outliers with like zeros or really low marks, and because they're dragging the mean down more than the median. So it's most fair to say here's the mean and the median, so that you can account for those outliers. I've got a little visual here. Drag my picture over here of a distribution of data and how outliers can affect it. So in a symmetric distribution, the mean, median, mode all kind of lie along the same central value. They might not be perfectly equal. Like, this diagram is of a perfectly symmetric distribution. But, you know, if you were to measure the heights of people in your class, that's a good example. Usually marks in a classroom can be fairly distributed symmetrically. But those kind of things, the mean, median, mode would be pretty central. So when a distribution is non-symmetric, so we say that the distribution is skewed, the mean, median, mode will differ. So in a positively skewed distribution, the mode will be the lowest of the 3. So this guy here is a positively skewed distribution, because if you can see, like, it's like the tail of that data has been stretched out in the positive direction. And in cases like that, where you have, you're going to have some very high values that are outliers, the mode will be lowest, the mean gets dragged along because of those high outliers, and the median will be kind of in the middle. And then the last guy is a negatively skewed distribution, because the lower values are dragged in the negative direction. You can kind of see it's like a perfect distribution with this end dragged to the left. And this is like a classroom where you have some people with like zeros, because those zeros drag the mean down. The mode stays about the same, and then the median kind of gets dragged a little bit, not affected as much as the mean. So that's how outliers can affect a symmetric distribution. Keep those definitions in mind of a symmetric distribution, a skewed distribution. All right, here are some guidelines to help when you're analyzing data with outliers. So like a class and trying to get an idea of how your class is doing. If the data is roughly symmetric, mean or median both do a decent job, because as we've seen in a symmetric distribution, those are all the same. If the data set is small and there appear to be outliers, use the median. And hopefully you're convinced of this, because I gave you guys a small set of 6 values with one extreme outlier, and you guys saw that removing the outlier really, really changed the mean, but the median was still the same. So if a set is small, best to use the median. Where the mode can be helpful is if the data is not numeric, it's qualitative data, or if the frequency is the most important thing, then you can use the mode. All right, let's move forward. I'm going to show you guys how to estimate mean and median when you have some group data. because not all the time you're going to get a huge just like set of data, all the raw data values. A lot of times you might come across some data that's already been kind of grouped. You might get a histogram, or you might get a table like this, where you don't know the specific ages of these people, but you know there's 10 between 16 and 20, there's 18 between 21 and 25, et cetera, et cetera. So I'm going to show you guys how you can estimate mean and median for group data right now. The key is you use the midpoint of each interval. So for example, I don't know. I know that there's 10 people between ages of 16 and 20. I don't know what their ages are, but I'm going to assume they're all the midpoint of that interval. I'm going to assume they're all 18. That's the midpoint of 16 and 20. And then the same thing. I don't know the ages of these 21 to 25s, but I'll assume they're all 23. And then the midpoint of each of these guys, 28, 33, 38. So you kind of assume their ages. To find the mean, so in this case, I'm going to use X bar here. And I'm going to say, I'm going to use an approximate symbol because we don't exactly know what these ages are. We're making an estimate. It's the sum of the frequencies times the midpoints divided by the sum of the frequencies. So why does this make sense? Well, the frequency just tells you like how many people are in these age groups, right? And if you added up these frequencies, 28, 40, 50, that just gives you the total number of values, right? So it makes sense when we're calculating our mean that this sum of frequencies would be on the bottom. It's just like our total number of values, right? And why do we multiply F times M? Well, we don't know the ages of these 10 people, 16 to 20, but we assume they're all 18. So we assume we have 10 people that are age 18. And if you added all those up, it'd be like multiplying the frequency times that age, so 180. So it gives you a way to add up all those values, multiplying the frequency by the midpoint. So let's do that. Let's actually, I have another slide here where we're going to estimate the mean. So I'm actually going to save this and just continue on the next slide. So I'm going to get that stuff we had in there. We had 18, 23, 28, 33. Now you guys can do this on your table at home. Maybe you've already got these values done. We had 50 people, 180, 18 times 23, 414. 12 people aged 28, 336. I think this is 264. Yep. And 2 times 38 is 76. And so we add all those up, and we've got a good estimate for the total of all the ages by using the midpoints of these intervals. So I got 1,270. So using our formula to get the mean age of this group, using the sum of the frequencies times the data, the midpoints, divided by the sum of the frequencies, the total of all these products was 1,270. That's like an estimate for the total number of all the ages. And we had 50 people. That's the sum of all the frequencies. 1,270 divided by 50, 25.4. So we've estimated the mean age of this group of people by using the midpoints. So it should be a pretty good estimate. For the median is the, in this case, because we know that there's 50 values and that's even, right? We know there's going to be 2 middle values that we're going to have to average. We don't know what those 2 middle values are, but we know what interval they're in, right? There's 10, it'll be the, well, so I might write this first. The median, there's 50 values, and we know there's going to be 2 middle values. Those 2 middle values will be the 25th data value and the 26th data value. And we know that we'll be averaging those two guys. Where are those 25th and 26th people? Well, they're in the 21 to 25 age group. But why? Well, we have 10 people age 16 to 20, 18 to in the age group 21 to 25, and that makes 28 people. So we know the 25th and 26th person are in this age group of 21 to 25. We're assuming the midpoint was 23. And so an estimate for the median would be 23 plus 23 over 2, or just 23. And that's just an estimate. A way to find to estimate the median using group data. Now, maybe you're saying, well, those 25th and 26th people would be towards the end of this interval because there's only 28 up to that point. So maybe the median might be closer to 24. That's sound logic, I would agree. But we actually don't know how those ages are distributed within there. So 23 is just an estimate. Right. The last thing we have to talk about is weighted means. And this is really important as far as, marks being calculated on a report card. Many of you guys have probably got a mark book report from your teacher before and actually have seen weightings. People who don't know how weighted means work, just might take all the marks for your whole semester, every test, every quiz, every maybe exit pass your teacher did, every small little thing, average those up and say, well, why isn't my mark this? I got 90 on all these things. I just didn't do well. I got a 60 on my test. But I got 90 on all these things. Why is my average closer to 60? Well, it's because your test is weighted more. Calculating a weighted average is a lot like calculating the mean for group data. But we're going to use weights instead of midpoints. So here's an example we're kind of all should be familiar with. Every course is a little bit different, but your term mark is always broken down by weights in terms of these 4 categories. And this is just a guideline. Teachers try to stay as close as they can in their own way. But in this particular course, knowledge understanding is weighted 30%, application 25%, communication 25%, and tips 20%. And you'll notice all those weights add to 100. But we're weighting knowledge understanding higher than we do tips. In an applied level course in the Ontario curriculum, thinking, inquiry, and problem solving, we would weight a bit lower than just the maybe application and knowledge understanding. But for a university level course, we might weight the thinking and problem solving a bit higher. So this student got an 80 with all the knowledge and understanding stuff, a 70 with the application, a 70 with communication, and a 90 with their thinking and problem solving. And we want to estimate we want to calculate what their mark is using these weights. If all the weights were the same, then we just average their marks, right? But the weights are different. We want to count knowledge and understanding more. So the way we do that is we multiply this mark of 80 by a weight. And by weighting knowledge and understanding higher than the other guys, it's going to essentially count more. As a teacher, when I'm weighting individual assignments and quizzes and tests, I have to decide how much do I want to weight this. Did I not do a great job of explaining that topic, or did I make a mistake on making a question for this test? Should I weight this a bit lower? Those are all things that go through my mind as I assign weights. But the formula for finding a weighted mean, and sometimes the symbol we use for weighted mean, you might see X bar with a subscript W or a mu with the subscript W. It doesn't matter to me, but we're finding a weighted mean here. It's the sum of the weights times the data value assigned to that weight divided by the sum of all the weights. And so here, do I have a second screen for this? I do. So let's find the weighted average for this guy. I'm just going to do it on the screen here. So let's use our table here. So 30 times 80, 2,400. 25 times 70. I probably should be able to do that in my head, but I'm not going to risk it right now. 1,750. We get the same for communication, and then 1,800 for tips. We'll total those up. 2,400 plus 1,750 plus 1,750 plus 1,800, 7,700. And now for this particular example, we can get an idea of how this student did. That's 7,700. The total of all the weightings, the weighted marks, was 7,700. And the total of all the weights was 100. The average for this person, 77%. Whereas if we just average all those marks together, it's pretty easy to see. You would just get 80 because you're, sorry, what'd you get? You wouldn't get just 80. As soon as I say easy to calculate, I make a mistake. Divided by 4. You get 77.5% as if you just average those guys. But the weighted average about 77%. So this time it actually came out pretty close. But this is a way to be fair, actually. You know, like some students might struggle with problem solving, so we might weight that a little bit lower for certain courses. Let's do an example, and you can try this on your own if you would like to, or follow along with me. So, you know, depending on the course you're taking, in the data management course, the final exam is worth 20% of the final mark normally, and 80% would be your term plus a 10% performance task. But here, we'll just say the term is 80, and these are the weights, and the exam is worth 20%. And those are my 2 weights in this case. So just the 2 weights. So Bort had a 70 going into the exam and got an 80 on the exam. We're going to calculate its final mark. So a lot of students, you know, towards the end of the semester, when they're getting closer to the exams, are always kind of crunching the numbers. Well, if I get this in my exam, what will my mark be? And, you know, what can I afford to get on my exam so that my mark won't dip below a certain number? This is the kind of calculation that helps you, a weighted mean. So let's find Bort's final mark using this weighted average. So sum of the weights times your values over the sum of the weights. So here we only have 2 weights. We have the term. So weight 1 is 80, and Bort had a 70 for that term going into the exam. Our second weight is 20, and he got 80 on the exam. And the sum of the weights on the bottom, 80 plus 20. So I'm actually just going to switch to a different color, and just for this one, highlight that here are my 2 weights, weight 1 and weight 2. That's my first data value, my second data value associated with those 2 weights. And then on the bottom, adding up the weights. So you can do that in 1 step if you like. You can do it in 2 steps. I think I'll just do it in 1 because the bottom is just 100. So it's pretty easy to just do all this at once. Plus 20 times 80 divided by 100. So we can see that the student got an 80 on the exam, and it bumped their mark up to a 72. Excuse me. So yeah, it did much better on the exam, but only pulled up their mark of 72, 2% to 72. That's because like the term's 80%. The exam is only worth 20, so obviously that 70% term will be weighted more than the exam. So it only brought it up a little bit. So that can work for or against you. You know, it's harder to bring your mark up, but it's also harder to bring your mark down. So if you had a rough exam, your mark would not go down too much. All right. Second part to this question. So let's say Bort had a 70% going in an exam. We already saw that an 80 got him 72. But let's think maybe before the exam, you know, Bort's thinking, hey, is it possible to get my mark to 75%? What do I need to get in the exam to do that? Well, we can find out. And so you could also say, well, what if I didn't want my mark to dip below 65? What could I afford to get on my exam? So lots of useful ways to do this. So in this particular problem, I might write it out this way. So the weighted average is my weight 1 times data value 1 plus weight 2 times data value 2 divided by the sum of my weights. Now, if we think about this in this particular question, what are we given? What are we asked for? We actually know the weighted average. We want to get 75. What we don't know is the exam score. We're actually looking for X2. And we know everything else, right? So let's plug in all that stuff. And then what we're going to get is an equation that we can solve for the exam mark. So we want to get a 75. Weight 1 is 80. We still got a 70, so that's not changing. Plus weight 2 is 20. Let's just let our exam mark be X instead of X2. And then the sum of the weights was 100. So we have a little equation to solve. It's not a very hard equation. We can multiply up the 100, multiply both sides by 100. So we get 7,500 equals 80 times 70 is 5,600 plus 20x. So we've turned this into a little two-step equation that you guys have solved or started solving even before grade 9. So let's solve this guy. So we'll subtract 5,600 from both sides. 1,900 equals 20 times x. Divide both sides by 20. And we get 95. So actually, it is possible. 95% would raise it up to 75. It is mathematically possible. I cannot spell, raise it to 75. So a nice little example applicable for you guys, because I'm sure many of you guys have been in that situation where you know your term mark and you're just going to the exam. You want to know what you need to bump up your mark or to not drop too much. All right, next steps for you guys. So now that we've reviewed mean, median, mode, when they might most be helpful to calculate what an outlier is and how to estimate mean and median from group data and calculate weighted means. Those of you guys with your textbook, page 263, lots of practice questions for you guys. As usual, I have a PDF of those questions as well. Where we're going next, the next 2 lessons, we'll spend 2 lessons talking about measures of spread. And then we'll have a little assessment on calculating statistics and make sure you guys are rock solid with the things we've learned about for this lesson and our next 2. So I hope you enjoyed that. I hope you guys are staying well. Have a great day, and we'll see you soon.